Our next topic is trigonometric integrals, and sometimes I've heard it referred to as a trig reduction. It has to do with the fact that we're reducing the exponents on the trigonometric function. But trigonometric integrals is the name of the topic, and there are some basic identities from trigonometry, from your glory days in basic trigonometry, that are going to come into play. And you're going to use these so frequently that they're going to come back up into your short-term memory. So you'll use them over and over and over again, and these will happen many times in the work we're doing with trigonometric integrals. This is a really key stepping stone to what we're going to be doing, because the next section up, when we do a special type of trigonometric substitution, what happens is you have an integral, you do trig substitution, next section up, and what you inherit from that process are trigonometric integrals. And so if you lose this piece in that chain, then there are going to be a whole slew of integrals now that you're not going to be able to handle. So this is a key piece of the puzzle, and it's one of the steps in the chain that gets us from some relatively complicated integrals back into things that you know how to do. So remember that sine squared is equal to 1 minus cosine squared. Cosine squared is 1 minus sine squared. Each of these four is a variation on the basic Pythagorean identity from trigonometry. Tangent squared can be expressed as secant squared minus 1, and then secant squared can be expressed as tangent squared plus 1. You got to be careful with that. I always try, now of course you can write these in several different ways. As a student, I always try to use this memory device. With sine and cosine, the 1 comes first, and I think this will help. With tangent and secant, the 1 comes last. Of course, you could write this different ways, but if you always write them this way, that'll help you to remember, if you need a memory device, what sequence these, or what is the arrangement of those terms and those identities. So these are going to come into play. The idea is, if we have an expression involving sine squared, then we may, if we wish, express it as change it to an expression involving cosine squared, and so on down the list. Now, there's another technique that actually it's actually a calculus 1 technique, but I want to sort of brush through it again. And it's what I call, and this is not unique to me. I got this from a former instructor here at the college, Mr. Collings, but it's what I call, or what we call, the 1 over a rule. And it's actually one of the basic forms. It just doesn't look like it. The idea is this: we know the integral of, let's say, cosine. Let's keep it easy here. Cosine of x dx. We know the antiderivative of cosine is sine of x plus the constant. But the point is, if this argument has a constant multiplier, if this is a times x. So let's do a specific case. Suppose we have cosine, and let's say it's 4x. This is why I'm calling this the 1 over a rule. This coefficient is my lowercase a in this expression. Now, what you may do, if you wish, is go through the basic calculus 1 U substitution. It's the same way as is always done. What I'm going to do is, I'm going to essentially call this a basic form. Let's see what we have here. So let's just do a U substitution. Let U equal 4x, it's the inner function. Du is 4 dx, don't want 4. And so to get rid of this 4, you see where the name comes from. To get rid of this 4, we write this as 1 over 4 du is equal to dx, and now the substitution is exact. And so when you substitute, the constant multiplier is 1 over this coefficient. So this is 1 over now the integral of cosine, and 4x is u, dx is du. That's a basic form. So this is 1/4, the antiderivative of cosine is sine. And then you go back to the original variable. And so what is the net effect of this process? Notice that if this is not present, the antiderivative is simply the sine of x without the 1/4. But if this, notice how this argument stays the same. Do you see that? This argument stays the same in your final result. But you have a multiplier of 1 over 4, and it should be pretty clear. There's nothing magic about 4. This can be any coefficient. So if this had been 6, this would have ended up being 1 over 6 and 6x. If this had been 9, this would have been 1 over 9 and 9x. And if this had been, this is a little bit more cautious here, if this had been a fractional, let's suppose this is 1/3, then this would still be 1/3 x. But now this becomes 1 over 1/3, or we may simply write 3. If this is 2/3, this is 2/3 x, and this is 1 over 2/3, which is 3/2. And so in any event, what we have is the constant multiplier here is the 1 over a. That's why this is called the 1 over a rule. And there's nothing magic about cosine. So in an exactly similar fashion, if we have the antiderivative of e, let's say that's raised to the 7x dx. Well, we should be able to go directly to the final result, because the antiderivative of e to the stuff is e to the stuff, but we have the constant, we have the 1 over a, 1 over 7. And so there's nothing magic about the exponential function, there's nothing magic about cosine. All functions have this property that we can, if the argument is a times x, actually it can be anything. It can be ax plus b, any linear expression. But to our point, if this argument has a coefficient, then when you find the antiderivative, you maintain that argument, but that's the 1 over a rule. That's going to come into play over and over and over and over again for our work in these trigonometric integrals. It actually comes into play over and over again in all sorts of places, but in particular in trigonometric integrals. So that's going to happen, and so I think that's worth brushing through. And so from now on, from this point forward, let's get back to the original problem here. All right, so the original problem, this was 4x, this is 1/4, and this is 4x. You may, if you wish, go from here, do the substitution, do this work, write this value, go back to the original, and if you do that, that's fine by me. But as far as I'm concerned, you may, if you wish, go from here directly to here without showing any of this intermediate work. If you can do that, not only will I allow it, eventually I sort of start to expect it. You should be able to go from here to one, though, use the 1 over a rule without any intervening. You could, if you want, go off to the side and do the U substitution here. But I would eventually begin to expect you to be able to go from here to here without showing any of the intermediate work. So that's kind of the background for these trigonometric integrals. There's one other small tidbit, and then we'll actually start the calculus portion, or the new calculus portion. Everything here really is sort of a review of the background. The one other piece is this. There are two identities that are going to come into play. And they're called half-angle identities, and you'll see why here in a bit. Sine squared can be expressed as 1/2 times the quantity 1 minus cosine 2x. This argument is half of that argument. And in exactly similar fashion, it can be shown that cosine squared, this is actually a consequence of this statement if you look where this identity comes from. For us, we're not worried about trying to verify it or trying to establish it. We're going to accept these as bald facts. Sine squared is 1/2 of the quantity 1 minus cosine 2x. Cosine squared is 1/2 times the quantity 1 plus 2x. Notice, they're exactly identical. The good news is they're identical. They're almost exactly the same. The bad news is they're almost exactly the same, and it's relatively easy to get them confused. As a student, This was the rule that I used as a student to try to keep this straight. Eventually, you do this enough, it becomes second nature to you. But as a student, when I can still recall, way back in 19... I can still recall that the rule I used was this. Usually, the only place you use this identity, or the place you use this the most for our purposes, is working antiderivatives. And my memory device is the antiderivative of cosine is positive, the antiderivative of sine is negative. Now, this isn't the antiderivative, that's not the point. But cosine, the integral is positive, sine, the integral is negative. That was my memory device for remembering this, because typically these get used in the process of finding an antiderivative. So by hook or by crook, those four need to be up in your short-term memory, and so do these two. And we're going to put those to good use when we start to talk about these trigonometric integrals and the actual computation of them.